Alright, welcome back. We're going to finish up with our discussion of pipelines. Hopefully you can recall from last discussion the general architecture, but we're going to go ahead and do a quick review just to make sure everyone's on the same page. Over here we started our instructions in the fetch, and each instruction is going to have 5 stages: our fetch, our decode, our execute, our memory, and then our write back. And in between each stage we have what's called the pipeline stages, which store the state or the result of the previous stage. And the label of each of these pipeline stages is the previous stage name / the next stage. So this is instruction fetch, because instruction fetch on this side, / instruction decode, because instruction decodes on this side. So what fetch does is it reads for the program counter, goes into instruction memory, reads the instruction, and puts it right here, as well as calculate PC plus 1. Boom. After that is completed, in the next cycle, the instruction is read, is broken apart so that you can find out which registers you're reading from, and it reads those values from the register file. It breaks up to find the offset in case we need that, as well as the destination register and the opcode, and it just forwards along PC plus 1. That's all decode does. It basically breaks up the instruction and reads the values that are necessary from the register file. And execute is where we execute or do the arithmetic logic units. So we have our ALU. If we're doing a standard add, we're just going to take the 2 values. If we're doing a address calculation, then we're going to base it off of the offset. Notice that the PC plus 1 plus offset goes to this adder up here, which then stores the target of where we would jump if the 2 are equal. And the ALU result is stored as well. We forward the value of B in case we need to write it to memory. And of course destination and op as well. And the next stage is memory, where we deal with memory, and if it's a memory instruction, that is where we actually either read from memory and load the value over here, or we store value B into data memory. Also during this instruction, if the equal is true, then we are going to jump back and tell this to this mux, which will tell this program counter to update to our new target. Then after memory, it goes to the write back, where if we're doing an add or NAND or load word, we're going to find out which piece of data we need to store in the register file, either the ALU result or the data we just loaded, and then what register we're loading to, so destination, it goes in and load that into the register file. And so those are the general 5 instructions. I'm not going to go through the specific example of the instructions flowing through this pipeline, but notice that they do flow, and at some point we're executing a piece of up to 5 different instructions. The idea being here that if you can break it up into 5 parts, you can increase your clock cycle, which will increase performance overall, and the instructions flow from the left to right in order. If you need all of that again, please go ahead and review from last class. Here's a time graph. Notice that we are fetching an instruction every cycle, and then once the pipeline gets full, we're completing them or writing them back every cycle. So the idea is that as the number of cycles increases, our CPI, or our cycles per instruction, will approach 1. But what can go wrong? Well, data hazards are the first thing. Notice that register reads occur in stage 2, aka decode, but it doesn't write it back to the register until stage 5. So let's look at here. What if the instruction is in this slot right here, needs to write to the register file, needs to write to a register that this instruction is trying to read from? It doesn't have the value yet. That's called a data hazard because it doesn't have the data yet. The other one you'll notice is called a control hazard. Notice that the offset is not calculated until memory, yet we've already fetched 2 instructions. So if we are jumping to a different PC, that means that these 2 instructions are possibly not correct. That's called a control hazard because we haven't controlled where we need to read our next instruction from. And let me make sure I'm still recording. Good. By the way, I am still locked out of my email. Hopefully they'll be fixed today. And exception. So the last thing that can happen, or don't look at the pipeline, you have to think of this about from a computer standpoint, is an exception may come in to interrupt the processor saying, hey, you need to deal with something. An example of this might be when you hit a key on a keyboard and now the computer's like, okay, the user finally hit a key on the keyboard, we need to deal with that. Or maybe it got some data from the network or whatever else is happening. So when this happens, the processor needs to be stopped from what it's doing and go from there. So we need to handle in the hardware, how are we going to stop or pause execution. But let's go back to data hazards. I've already talked about what are they when you can't get the data that you need yet because it hasn't been written back to the register file. But how are we going to detect them and how are we going to deal with them? Well, first let's go ahead and do a quick review again. How do we do it, or what are they? So in decode or reading, and in write back is where we write the sum. So if instruction's in memory or in execute and is writing a value to something that the previous instruction needs to read from, that's a data hazard because it hasn't gotten that value yet. Another example here is with the add and the and. Notice that the add doesn't write the value back until write back, but the and needs it during this cycle, during decode. And we can't send information back in time, at least not yet, so we need to somehow fix this problem. Well, how do we detect it? Well, you have your destinations right here, which is great. We're just going to forward that to 3 different registers right here, and then maybe we can do something with that to detect if there's a problem. But once we detect it, how do we handle it? Well, one, we could try and avoid the problem and just tell the compiler to fix it. Common idea, but as we'll find out, it's going to be terrible. We could detect and install, where we detect the problem and then just throw in no ops until the problem goes away. That does work. And then detect and forward, basically, once we detect the problem, see if we can fix the pipeline. You know, if the value's in the memory stage, maybe we can just write it over to execute so we can just use it then. And we'll get to these 3 in a moment. So the first one is, of course, avoiding the hazard. Have the programmer or the compiler knows about the implementation of your hardware and go ahead and throw in some no-ops where necessary. So add here, and the compiler says, oh, I know our architecture needs 2 no-ops here, so I'm going to throw in a code, and then everything's going to work just fine. Well, that's nice because that means our hardware doesn't have to do anything. But the first problem is our old programs, aka legacy code, no longer run correctly on a new implementation because our longer pipelines need new no-ops. This turns out to be the absolute worst idea because people who have programs that are working do not want to recompile them, especially recompile them for different pieces of architecture. For example, once you have Microsoft Office on a CD, you don't want to have Microsoft Office for this processor, Microsoft Office for this processor, the game for this processor, etc., etc., etc. This turns out to be very unacceptable, not just for the end user, but also you might have a very antiquated piece of code that runs on a very specific piece of antiquated piece of code that they've been running for a very long time that no one wants to update. And now what you're asking is everyone's going to need to update their tool chain, probably have to then update their code so it conforms to the new tool chain. And when I say tool chain, I mean the new compiler, the new build environment, the new architecture. And that's going to cost a lot of money as well. No one's going to want to do that, so no one's going to buy your processor. Also, another problem that ends up being is that Intel Epic, which did take this approach, and wanted to put no-ops in, and then often 25 to 40% of your instructions are no-ops. So how many of you have heard of this? Probably no one. There's a reason why. This was a terrible idea. So this basically just tanked, and Intel dropped it and just went right back to x86. Program execution is slower because you have all these no-ops running around. CPI is one, but that's fake because 25-40% of those instructions are no-ops, so that doesn't really count that your CPI is 1. The next idea is to detect and install. Basically, instead of having the compiler write the no-ops, have the processor detect when you need to put the no-op in and then go ahead and do it. So, back in here, notice that we had our 3 registers to signify the 3 different destinations in the future, or the instructions that are currently executing. Here are those 3 different registers of what values are about to be written to. You would then have a comparator for register B and register A, and those would put out a line to say if a hazard has been detected. So you'd have 3 on top and 3 down here. Only 2 are shown because we didn't show this one over here. And so these 3, you then have 3 lines, and you'd have to basically combine the 3 lines and detect if any one of them are a hazard. And we could use something like this in order to do the detection for an individual register. Once you've detected that it happens, you keep the current instruction fetch and decode and then pass a no-op. For example, let's say you have that add and then the and. Hey, that got a little messed up. Let's get rid of that 5. Is right here. Oh, there's going to be a hazard because the and needs to read from the 3, but this add is writing to the 3. So what happens is you pass a no-op. So basically the idea is that you pass a no up down here, and to execute, add is going down here, and is being held over here. How do we actually do that? Well, you have little enable bits for your program counter and for your pipeline register, and when those different registers are disabled, that means their state is not going to change. So you may fetch the next instruction, but you're not going to store it. So you're effectively not doing anything during that instruction, which is perfectly fine. You again pass the no up again because the value still has not been written back to the register file. Now in this next instruction, we generally say that once add is in write back, we're going to go ahead and say that there's no hazard because most register files are allowed to write and read at the same time. There we go. And then the add occurs. Well, that add's messed up, but let's move on. So what happens here is write back. This is just like before, except for now we have detect 2 hazards. So this AND instruction stays in decode for 2 additional cycles. So it takes 7 cycles instead of 5 in order to complete. Now, what's nice about this is that all your legacy programs still run, so people will still use your new processor, and you have, at least hopefully most of the time, increased your performance because you're hopefully not having this problem too often. But it turns out, is this always necessary? No, not always. We could always reroute the result at some point and then get the data when it's later. And this can be completed or decided in the decode stage, and we'll go ahead and show that. But be careful because there are situations where you're still going to have to stall, and we'll do an example there. So we detect there's 4 different types of hazards in our architecture. We'll go ahead and show I think 3 of them. We'll have a little bypass data paths, and again beware stalling may still be required. So let's go ahead and look at these instructions. Well, you have an add. You're going to add 3 and 2 and write to 3. Okay, we're good. We're going to AND 4 and 3. Well, there's your first hazard because we have to read from 3, but it's going to be written back here. And then we're going to add 4 and 3 again after we've ANDed it. There is also a hazard here because this 4 needs to be read here, as well as this 3 needs to be forwarded down here. And then we're going to add 6 and 3. Right here we don't have a hazard because by this time the 3 has been written back and the 6 is good. But if we want to move L, we are going to have to forward the value 3 to here. And then let's see what we're doing. And then, I'm sorry, actually there's no problem right here because we just need to forward the 6 in order to read the address. So we got that. Next, we have the 6, which again you're going to have to forward from the AND, which is okay. But the problem here is we're loading into 3, which means we need to wait for memory to read to load into 3 before we can calculate the base address here. And that unfortunately will require us to stall. Alright, let's go take a look at this. So we have the add and the AND, and we're going to go ahead and forward the add and the AND, but we have labeled it as a hazard 1 because we need to forward the result of this add back to that and that's what it's going to look like here. So we take that and we move it to this mux here, which goes into the ALU. Let me go back a slide just to show you that mux was not here, but we're now going to need that mux in order to know that we need the value from here forward over here. Notice that this hazard bit would turn that mux on, and the hazard bit's determined inside of decode. This add has a hazard 2 because this AND actually needs to forward up here, right there. And actually, if you're paying attention, I think this AND needs to forward up here as well. Actually, it does show you up here. Great. So we have those correct values, and then now the value is written back here. This instruction would have had a hazard, but we were able to read and write at the same time. Now the move L or the move S is going to have a hazard with the move L. If you recall, move L is writing to register 6, but register, register 3. Yeah, these values are wrong, sorry. So this needs to write to register 6, this needs to write to register 3. And then this needs to be based off of 6, and then there we go. So this is going to load to 6, and then you're going to have 6 plus offset. That's the actual error. Oh, I'm going to have to fix a lot of these slides. Sorry about this, guys. Let me go do this real quick. This will make way more, oh, that makes way more sense. 6, 3, all right. Now That way all the slides will line up and make sense. So the hazard's detected with the 6 because you have to read from of 6 in order to get it, but 6 is what's being written to by the move L instruction, but you won't get that value till data memory. And this will make a little more sense in a moment. So we do go ahead and pass the no op because we are going to have to stall for a moment. And the reason for that is if you had move S over here to store the word, it would not be able to compute the result because the base, aka the 6, has not been loaded to memory. So if this move L needs to load from memory, you got to wait for it to at least get back to write back before you can start executing. Alright, I gotta fix all these slides. Whew. Now the move S is here, hazard 3, knows that the move L does have the value. Move S is in this stage. It has the wrong value from the register file, but at least we know now we can forward it because the data has been loaded from memory. Alright, and then we can continue on. Alright, let's go ahead and take a break, and then we'll talk about control hazards.